Hey everyone, I am Dr. Surjit Singh. In this video on Python via example, we shall discuss about some sorting methods. Let us begin. In this session, we will learn about the three sorting methods, the bubble sort, the insertion sort, and the selection sort. We'll know about the stable sort and about the in-place sorting. We'll find their time and space complexities and compare them. Sorting is the most important application in data processing. It helps in faster searching of a key item present in a list, comparison of two lists, median of a list, and top few entries in a list. Simplest way to sort a list is the bubble sort method. We are given a list for sorting. Number 4 occurs thrice. Let us mark them in different colors in order to study their movements during the sorting of the items of the list. An example of bubble sort in daily life is in which the students stand in a row as they come to the assembly and then they repeatedly swap their positions with the persons next to them so that those who are shorter in height come to the front of the row. In bubble sort, we follow the bottom-up approach in which the size of the sorted list increases by 1 in each iteration. We call it the decrease and conquer approach. We save the index of the last item of the list and run a loop over the items of the list starting from the beginning. We will bring the smallest item at index I, for which we start a reverse loop from the end of the list. We compare the items at j and j minus 1. We do nothing in the loop over j if the items are already in order or if they are equal. But if they are in the wrong order, we swap them. 0 will swap with 8 towards its left and then with 4, 1, 4, 6, 1 and 3. Loop over j continues as long as it is greater than I. When j becomes equal to I, we come out of the loop over j. We have now sorted sublist up to I items of the list. In the next iteration over I, it becomes 1. This time, the first pair that is in the wrong order is of 8 and 4, so we swap them. Next pair that we are required to swap is of 4 and 1. We swap them. After this, we swap 6, 1 and 3, 1. With this, we have sorted the first two items of the list. For I equal to 2, the pairs that we swap are 8, 7, 6, 4 and 3, 1. We have now sorted the left sublist up to I. In the next iteration, only swap is between 6 and 4. In the next iteration again, there is only one swap. List is fully sorted, but we have no way of knowing it, so we continue with the iterations over I till we finish with the loop even when there are no more swaps. We notice that the old relative order of the three fours is unchanged, so we say that bubble sort is a stable sort. All the swaps that we carried out between the items had been within the same list, so we say that bubble sort is an in-place sorting method. The if statement in the program is the basic step of sorting. It judiciously interchanges positions of items of the list. Every swap takes a constant time that depends on the processor we are using. When I is 0, the loop over j calls the if statement n-1 times, where n is the number of items of the list. When I is 1, the loop over j runs once again for n-2 times and so on. So total number of times for which we call the if statement is n into n-1 by 2. When n is very large, 1 is negligible and therefore the if statement is called n squared by 2 times. In the worst case scenario, we swap numbers in each iteration of j and each swap takes a constant time. Therefore, the time complexity of bubble sort is of the order of n squared. Of course, if the original list is nearly sorted, there will be less number of swaps between the items and the time of sorting will be less. We swap the items within the original list, so except for a few constant memory locations, we do not use additional memory proportional to n. So space complexity of bubble sort is constant, not dependent upon n. Another method of sorting is the insertion sort. This also follows the decrease and conquer bottom-up approach. In this method, we start with a loop over I from the beginning of the list. Consider it as a sublist for sorting. We copy this item to pivot and define j to be I-1. As j is negative, we do not enter the while loop this first time and restore pivot back to its original position. This one element sublist is sorted. We will now insert remaining elements of the list one by one at their proper positions in this sublist. In the next iteration, I becomes 1. We save the item there as pivot and assume it like a hole in the sorted sublist. In order to fill this hole, we start with j to be I-1, and while its value is greater than or equal to 0 and the item there is greater than the pivot, we shift right the item at j to the hole. As a consequence, the hole shifts left. We decrease j by 1. J is now outside the list, so the while loop ends. We fill the hole with the pivot and the sublist of 2 items is now sorted. In the next iteration, I becomes 2 and we consider it as a part of the sublist that we are sorting. We save 6 in the pivot and consider it as a whole. Starting value of j is I-1. 3 is not greater than pivot, that is 6, so we do not enter the while loop. 6 goes back to the hole, which was its original position, and the sublist of 3 items is now sorted. In the next iteration of I, we say 4 as pivot and consider it as a hole in the sublist. J starts with I-1. 6 is greater than 4, so we move it right to the hole and decrease j by 1. 3 is not greater than 4, so we come out of the while loop. Present hole is the position where we bring back the pivot. Sublist of 4 items is now sorted. In the next iteration, pivot is 1 and j is at I-1. To insert 1 at its position in the sublist, we have to shift 6, 4 and 3 right. 1 is equal to pivot, so we don't move it. We now move pivot to the current hole that is present at j plus 1, which is its desired position in the sorted sublist. Next number that we insert in the sublist is 4. 6 moves to hole and the loop terminates. Pivot goes to the hole. In the next iteration, pivot becomes 8. It is the largest element of the sublist, so it comes back to the same position. Next pivot is 0, so all items move right one by one, and pivot goes to the new hole. Next, 4 becomes pivot. Now 8 and 6 move right, and the pivot moves to the new hole. 7 is the pivot in the last iteration. 8 moves right, and 7 goes to hole. With this, the loop ends. The list is now sorted. Relative order of the 3 4s remain unchanged, so the insertion sort is also stable. It is also in place because the items move within the same original list. Movement of items is faster than swapping of the items that require 3 moves. So insertion sort is faster than bubble sort. However, once again, we have a loop within a loop for which maximum iterations in the worst case are n. Therefore, the time complexity is of the order of n squared. When the list is already sorted, we do not enter the while loop at all. So, in the best case scenario, time complexity is of the order of n. Like before, space complexity is constant. Selection sort is the best method so far because in this we carry out long range swaps. This also follows the decrease and conquer bottom-up approach. We find the position of the smallest item in the list and bring it to the desired position. Initial value of I is 0. We save it as the initial position of minimum item. we start a loop over j starting with I plus 1. As 1 is less than 3, position j becomes the new minimum item position. We will make future comparisons with this number 1. For j equal to 2, the item is 6, which is not less than the item at min pos, that is 1. So we do not change the minimum position. Items 4, 1, 4 and 8 all are not less than 1. But when j is 7, the item there is 0, which is less than 1. So 7 becomes the new min pos. We will make future comparisons with 0. Neither 4 nor 7 is less than 0. With this, the loop over j ends. And we have selected the position of the minimum item. In order to bring 0 at the beginning of the list, we swap it with 3, which means that we swap the item at I with the item at min pos. At this stage, we have sorted items up to I. In the next iteration, I becomes 1, which is also the initial value of min pos. Starting with j equal to 2, we find that no item is less than 1, and we come out of the loop over j. Item at I is the minimum and we swap it with itself. For I equal to 2, loop over j finds out that minimum item is 1 present at min pos 4. So we swap 6 with 1. Next I becomes 3 and we save it in min pos also. Loop over j finds the minimum item in the remaining list, which is 3 at position 7. So we swap 4 with 3. Sorting is over up to position 3. Now we have to find number that will replace 6. Loop over j gives 4 as the minimum item at position 5. We replace 6 with 4. For I equal to 5, we find the minimum at position 7. We swap 6 with 4. Next, we swap 8 with 4, 6 with itself, 8 with 7, and 8 with itself. With this, the loop over I ends, and we get the sorted list. Selection sort is also in place, but it is not stable because relative positions of the three 4s have changed. With minimum swaps, this sorting takes minimum time. However, with a for loop within another, the time complexity is again of the order of n squared and the space complexity is constant. I took 500 random lists of size n each and found their average sorting times in microseconds by each of the three methods. We notice that the bubble sort is the worst. Selection sort is definitely better for larger lists and the difference will be appreciable when n is in millions. I took square roots of the execution times and found that they are linear in n, which confirms that the time complexity for all the three methods is of the order of n squared. In best case scenario, insertion sort becomes linear. However, selection sort is very fast for the worst case scenario. In the next videos, I'll talk about the faster sorting methods. In this session, we discussed three sorting methods: bubble sort, insertion sort, and selection sort. We defined the in-space sorting and the stable sort and differentiated the three methods with respect to them. We discussed their time and space complexities. I hope you liked the video. Please feel free to ask for further clarifications on my email address given below. I'm looking forward to your comments. Please stay tuned for more.